Hi, my name is Kevin G, and I'm here to present instrument classification of solo sheet music images. Our work is motivated by the following question. Suppose we have a sheet music image, and we'd like to determine what instrument the piece is scored for. Our goal then is to develop an instrument classifier that takes in a raw sheet music image as its input and returns a prediction for the instrument as its output. Our approach is driven by the desire to use as much data as possible. To do so, we take advantage of IMSLP, a large online repository of sheet music data. We also use transfer learning techniques from NLP, which involve pre-training on a very large set of unlabeled data and fine-tuning on a small set of labeled data. Here's an overview of the two main training components in our system. The first stage is pre-training, the first step of which is converting the sheet music image to words. The first step of converting to words is computing the bootleg score. The bootleg score is a representation of sheet music that encodes the positions of filled note heads relative to the staff lines. Note that this discards a significant amount of musical information, including accidentals and non-filled note heads. The bootleg score is a 31 by n binary matrix where n is the number of note events in the piece. The second step of converting to words is tokenization. We use two different tokenization methods depending on which model we are training. For word-based models, each column on the bootleg score is interpreted as a 64-bit integer, which then acts as a word. For subword-based models, each column on the bootleg score, which is 31 bits, is interpreted as a sequence of 4 8-bit characters. These characters are fed into a bypair encoding algorithm, which learns a vocabulary of subwords in an unsupervised manner. This type of subword tokenization is commonly used in many state-of-the-art language models. The second step of pre-training is to train the language model. In this step, we have two different types of models. Our word-based model is AWD-LSTM, which is trained to predict the next word in the sequence. GPT-2 is the first subword-based model, which is trained to predict the next word in the sequence. Roberta is trained to predict a set of randomly masked subwords. The end result of pre-training is a set of pre-trained weights, which we use to initialize the classifier in the fine-tuning stage. The first step of fine-tuning is to convert the sheet music image to words. This is done in exactly the same way as pre-training. The second step of fine-tuning is to sample fragments from the words. In this step, we randomly sample length L fragments from the labeled data. The two benefits of this are that it allows us to significantly augment the amount of data and sample in a balanced way. Here, you can see length 5 fragments being sampled from this list of words. The final stage in fine-tuning is to train the classifier. We experiment with 3 different pre-training conditions to determine their effect. The first condition is no pre-training. We train the classifier from scratch on the labeled data. The second condition is labeled pre-training, where first we train the language model on the labeled data, then add a classification head to the language model and fine-tune the classifier on the labeled data. The third condition is unlabeled pre-training, where first we pre-train a language model on the unlabeled data, then fine-tune the language model on the labeled data, and then as before, add a classification head and fine-tune the classifier on the labeled data. For our experiments, we selected 8 monophonic instruments which have a significant amount of data in IMSLP. The unlabeled data consists of all solo sheet music from IMSLP for these 8 instruments. For the labeled data, we randomly sampled 75 pieces from each instrument and hand-labeled them. Here are the results. The figure shows the performance of 4 different models. For each model, the different colored bars show the effects of different pre-training conditions. There are 2 things to notice about this figure. The first is that pre-training helps a lot. As we go from the green to the blue and the red bars, you can see that the results significantly improve. Also, the transformer models perform the best. We also explore the effect of data augmentation. To augment the data, we shift the bootleg scores up and down by a certain number of staff lines. Here you can see shifting up by 1 and shifting down by 1. We do this both at training and at test time. For test time augmentation, the predictions for the shifted versions of the input are all averaged to get the final output. Here are the results with data augmentation. This figure shows the performance of the models with various combinations of training and test augmentation. This figure k equals on of training augmentation and L equals on of test augmentation. The main thing to notice about this figure is that data augmentation significantly improves the performance of our models. As a final takeaway, to classify sheet music images by instrument, first we convert the sheet music into words, and then pre-train the language model and fine-tune it on the data. Doing so allows us to significantly improve the performance of our models. Additionally, using musically informed data augmentation allows us to further improve the performance of our models. Thank you for listening, and we welcome any questions at the poster session.